Believe it or not, the midterm exams are coming up. Functions will definitely teach all of you a very hard lesson. But all functions revolve around one core concept on the test. What is it called? Monotonicity. Monotonicity. To put it simply, it's the increasing and decreasing property. Rote memorization just won't work anymore. So in today's class, we'll thoroughly cover the 5 main ways monotonicity is tested and its essence. Let's master monotonicity all at once, shall we? Yes. All right. First, let's talk about the 5 main ways monotonicity is tested. I'll write it down. The 5 main test topics. The first one tests you on the monotonicity of specific functions. The second is abstract functions, which appear in major problems. Testing proofs. The third one, what does it test? It tests piecewise functions. The fourth one, it tests the composition of 2 functions. The fifth one, it involves a local absolute value and also includes a variable a and the monotonicity problems related to that. So for specific functions, what do they test? The first type of test, for example, involves linear, quadratic, and inverse proportion functions. Aren't these all things we learned in middle school? But they will take these middle school topics and build on them with more advanced concepts and knowledge to test you. Then in high school, we learned a few more functions: power functions, exponential functions, and logarithmic functions. Each and every one of these will be on the test. Let's go through them one by one, okay? Come on, let me help you build the framework first. Let's start with the first one, which is the monotonicity of linear functions. Related to linear functions, we have y equals kx plus m. What does its increasing or decreasing property depend on? Monotonicity means increasing or decreasing, right? It depends on k. So how does it depend on k? If k is greater than 0, the function is an increasing function. If it's less than 0, it is a decreasing function. Okay, let me give you an example to see if you can solve it. For instance, y equals 3m plus 1 x plus b. Now, I'm telling you, this function is monotonically decreasing on R. I want you to find the range for m. So, what kind of function is this? Linear. It's not necessarily linear. The type determines the solution method. What if it's 0? If it's 0, it's not linear. If it's 0, it's a constant function. A constant function is flat. It has no increasing or decreasing property. So since it's decreasing, it must be linear, right? Don't linear functions increase or decrease, right? So you said it depends on k, and isn't this k? So what do I just need to ensure? 3m plus 1 is less than 0. I solve for m. m is less than negative 1/3. That is my range. Okay, we've got linear functions. Second, quadratic functions. The form of a quadratic is y equals x squared plus bx plus c. What does the monotonicity of a quadratic function depend on? A and B. Right, it depends on 2 things. One is called the opening and the other is the axis of symmetry. They're different, right? So if my opening, A, is greater than 0, which way does it open? It opens upwards. My axis of symmetry is here. 0 equals negative b over 2a. Let me write it down for you first. If my a is less than 0, the quadratic function opens downwards. My axis of symmetry, x0, equals negative b over 2a. Are the intervals of increase and decrease the same? No, they're not the same. Let's look at this one first. Where does it decrease? The interval of increase or decrease refers to the value of x. Imagine an invisible x-axis. It means for which x values the graph is decreasing and for which x values it is increasing. It refers to x. So tell me, for which x values is it decreasing? Shouldn't it be from negative infinity to x0, it's decreasing, right? From my x0 to positive infinity, it's increasing. This one is different. From negative infinity to x0, it's increasing. From x0 to positive infinity, right? It's decreasing. Okay, the concept is very simple. But let's take a look at how quadratic functions appear in exams, some points that are particularly easy to get confused or make mistakes on, and the types of questions you'll be tested on. Okay. Let's look at these 3 problems related to quadratic functions. These are the points and areas of confusion where everyone easily makes mistakes when first learning. We'll use these 3 problems to explain it thoroughly. Let's take a look. First, observe 1 and 2. What's the difference between them? If you can tell the difference, you're halfway there. What's the difference? One is in the interval, see? The other is it's monotonically increasing interval. One is decreasing in the interval, and the other is the monotonically increasing interval is. You can also change it to decreasing. One is decreasing in the interval, the other is the monotonically decreasing interval is. If increasing is inconvenient, change it to decreasing. Aren't these 2 descriptions different? So what's the difference when solving problems? Let's see. When you study the monotonicity of a quadratic function, draw the graph first. Okay, let's draw the graph first. The quadratic function opens upwards. The axis of symmetry is x equals negative b over 2a. To put it simply, it's 1 minus m. So think about it. It's decreasing in the interval. Where was it originally decreasing? It was originally decreasing from negative infinity to 1 minus m. So what does it mean when it says it's decreasing in that interval? It just needs to be decreasing on your interval, right? As long as it's decreasing on your interval. In your mind, you have an invisible x-axis. It might not be there, and you don't have to draw it like this. You just have an invisible x-axis. Think about it. Originally, it's decreasing from negative infinity to this point. But then it tells me it's decreasing from negative infinity to 4. What does that mean? It means this interval is a subset of my original decreasing interval, right? A subset. As long as you're placed within my decreasing interval, then from negative infinity to 4, it will be decreasing. As long as you're within my decreasing interval, you'll always be decreasing, right? Isn't that right? Yes, it is. Convert it to a subset. To put it simply, your 4 just needs to be to the left of my axis of symmetry, right? Come on, can you write the expression? How do we write the expression? What about 4? 4 is less than 1 minus m. Can it be equal? Some might say, teacher who, for a quadratic function, can we write a closed interval here? Of course you can. For a monotonic interval, if this point is within the interval's range, it can be open or closed, it doesn't matter. Do you understand? So tell me, can 4 be equal to it? When it's 4, if you're not sure if it can be equal, just put 4 here. See? From negative infinity to 4, it's still decreasing, right? It fits the condition. Okay, so you solve the corresponding equation. Move m over m is less than or equal to negative 3. Got it? Got it. Okay, the first one is done. The second one is the same. The quadratic function opens upwards. My axis of symmetry, which we just found, is equal to 1 minus m. The monotonic increasing interval is this. What does that mean? Can we say that your interval is a subset of my increasing interval? No. In your mind, there's an invisible x-axis. Invisible. You don't have to draw it like this. It's invisible. Monotonic increasing interval means that all of the functions increasing intervals are just this interval. Yes. These 2 descriptions are different. Do you understand? My increasing interval is this interval. But what is my increasing interval itself? It's from 1 minus m to positive infinity. And you're saying it's from 4 to positive infinity. What does that mean? It means 1 minus m is 4, so m equals negative 3. So when you do problems, don't tell me you were careless. The essence of carelessness is not understanding these common pitfalls from the start. Is that clear? Come on, let's look at the third one. Observe the difference between the expression in 3 and the ones in 1 and 2. Right? Are we still necessarily studying a quadratic function? Not necessarily, right? Look, aren't these coefficients both 1? What's this coefficient? A. The type determines the method. It's not necessarily quadratic. What if what? It's 0, correct? So we divide it into the first case. What if a equals 0? Discuss it first. Only a quadratic can have a quadratic graph. If it's not quadratic, what graph would I draw, right? Come on, let me write it down. When a equals 0, fx equals x plus 1. X plus 1. It says it must be monotonically increasing from -2 to positive infinity. Is it satisfied? K is greater than 0. I just reviewed that. It's increasing on the entire set of R. It must be increasing in this interval. So it's okay. It meets the requirement, right? Okay, so we've kept this A. All right, second case. What if A is not equal to 0? If A is not equal to 0, to study its monotonicity, we should draw the graph first, right? For a quadratic function, the opening is either upwards or downwards. Two possibilities. -2 to positive infinity. Look, here's your sketch. Positive infinity is here. This one is definitely increasing, right? This one from here to positive infinity is decreasing, right? So is this graph a possibility? No. The graph must look like this. This one shows a decreasing trend towards positive infinity. I just need to ensure this one works, right? Okay, to ensure it, first, how do we ensure it? First, the opening must be upwards. Then we must ensure it's monotonically increasing from -2 onwards. It has to be increasing in this interval. What does that imply? As long as it's increasing on your interval, it's fine. Just like it's fine if it's decreasing on your interval. It's the same idea, right? Originally, I said we need to find the axis of symmetry. X equals -b over 2a. This means I just need to place -2 where? -b over 2a. Where do I put -2? Put it to your right. It's a subset. In your mind, there's an invisible x-axis, right? I put -2 here, right? Look, from -2 to positive infinity, it's increasing, right? So this means it's less than or equal to -2. Got it? Come on, let's solve this. Cancel the negatives, and we get 1 over 2a is greater than or equal to 2. Be careful to flip the sign. And we are solving this under the premise that a is greater than 0. Is that okay? Okay. Then we solve for a 1/4 is greater than or equal to a. The direction of the inequality sign doesn't change, right? We take the intersection with it since we're solving it under that premise. Okay, the result of these two is a is greater than 0 and less than or equal to 1/4. We've solved it. Hey, one a is here and the other a is here. What set do we take for these two? Between different cases, what set do we take? The union. To sum up, the range of a is from 0 inclusive to 1/4 inclusive. Got it? These three we just discussed are small quadratic problems that appear on exams. But it's not just about small problems, they also test you on big problems. You've probably seen the big problems recently. What kind of problem is it? Many of you find it really tough and can't solve it at all. It's in case analysis, moving axis with a fixed interval and fixed axis with a moving interval. This is divided into how to find the extreme value in the same direction and how to find it in the opposite direction. There are methods for all of them, but because of time constraints today, we can't go further into this case analysis. I've put all these methods and problem types into the 34 must-know function problem types for your midterm exam. You can comment 34 major problem types. I'll give you all the corresponding practice problems. Take them, print them out, and practice along with my course, all right? Okay? All right, class is dismissed.